All right. Good afternoon, everyone. My name is Özkan Can, and welcome to the last session today in Startup Central, which is called Rise of Robotics, Innovating the Future with IoT and AI. Before I start, I hope that you had a great AWS Summit in Berlin this year, and that you were able to find interesting talks and also make interesting connections that help you dive deeper into AWS in the future with your use cases. So what do we have planned for today's last session here? So it's all going to be about cloud robotics. If you've never heard about cloud robotics before, you can be pretty sure that you will hear a lot more from it over the next years. We are going to dive a little bit into robot development and mention some of the AWS services that you have at your disposal for creating your own robots. We are going to talk about robot use cases like collaboration between robots, but also robot-human collaboration and how these can be achieved and what AWS can offer you to help you with that. And last but not least, we have an extensive chapter about reinforcement learning and what reinforcement learning brings when we are talking about autonomous systems like robots. But first, let's talk about what we currently see. Robotics, as we speak, is undergoing a fundamental change in collaboration, autonomous mobility, and increasing intelligence. I mean, I'm pretty sure that everyone in the audience has heard about autonomous vehicles, smart cars in that regard, smart homes, smart IoT. Everything is becoming increasingly autonomous, increasingly smarter, and this is certainly due to the breakthroughs of machine learning and the possibilities of the cloud in the recent years. Currently, it is estimated that by 2023, that the amount of mobile autonomous robots for standard logistics and fulfillment processes will increase quite heavily. Right? By 2030, we expect that 20% of all mobile material handling will be handled by autonomous systems. And not looking in the future, but let's go 2 years in the past. Actually, Germany right now stands with 7.6% per 1,000 employees as the country with the most amount of robots used in manufacturing processes. And we are expecting this number to increase in the future. And robots are used in many different ways in many different environments. I'm pretty sure that you have all seen and heard about consumer robotics devices like vacuum cleaners, for example, from iRobot, which is one of our customers. And these help you to do your household chores. But also in logistics, healthcare, autonomous driving, we are seeing a great appetite for robotics and for future use cases that involve robotics. Right? We are at the beginning of an inflection point where the growth is estimated to increase tenfold across the next 2 to 3 years, right? So we are expecting, for example, mobile robots in the manufacturing industry by 2020 to increase to 332%, right? And in other industries, including household and consumer, to 798%. So it's going to be quite interesting journey where this will lead us as humans and as society, of course. Right? And similar to what the cloud did to machine learning, by providing you to scale, by providing you the ability to handle large amounts of data and give you large amounts of compute resources, the cloud can also help you to gain better insights and to develop better robotics applications for your use cases. Right? When we are talking about a robot, let's say, for example, a vacuum cleaner that might be, cleaning our household, how do we interact with it, right? There is not really a possibility for us to run behind it and try to find it in a closet or, under the bed. So we try to interact it with the most natural ways to interact with things, which is voice. So voice integration for robotics is a thing. When we are on the road, right? And we want our robot to do some course, we probably would use a mobile app that transmits this command and control information to the cloud and back to the robot to actually do his chores. In autonomous driving, we want to have vehicles that steer the road probably even better than humans are doing. And this is due to some technology advances with IoT and edge computing, so that we do have the latency that is required for these applications to react in a very time-sensitive manner. And finally, of course, collaboration, right? What happens when we do have multiple robots that need to coordinate with humans and also with other robots? Now, first, let's look into robotic development, and then we'll spend some time into collaboration and machine learning and what that gives us. So traditionally, manufacturing and developing robots is a very difficult process, right? You have to find the right hardware, the right equipment, you have to know about materials, you have to take into consideration hardware constraints and energy constraints, of course, because robots are typically powered by some kind of battery source. Right? So it makes it not easy for developers to start up a new experiment or a new development easy. We have to always run to our robot, change it, modify it, recharge the battery before we can actually get working with it. And this causes days spent in setting up and configuring where we actually would like to deliver business value and make a smart robotic device for our purposes. Since testing and development with real devices is only possible in limited scale, right? We are looking for simulation environments. Right? Typically, this is done by a simulation where the robotic is put into an environment, in a virtual environment, where we can apply different physical constraints, like gravity, for example, or like friction when the robot drives on a plane. And it requires, of course, machine learning expertise to create intelligent functions. So typically, the robot development cycle is divided into 4 steps. First, you select one of the robotics frameworks on which you would like to build your application. Second, you develop the application. Third, you test and simulate the application with real hardware, as well as simulated environments. And when you're ready, you can deploy and manage the application on the devices itself. At the reInvent last year, we announced a new service which is called AWS Robomaker. Robomaker is a service that helps developers to develop, test, and deploy robotic applications and build intelligent robotics by using the services that we provide inside the AWS cloud and with cloud services. Right. Firstly, the development environment. Right. In Robomaker, when you create a development environment, we create a Cloud9 development environment, so an environment that's basically available through your web browser that has already integrated a robotics framework that you can readily use, which is called the Robot Operating System, or short ROS, which I will go a little bit deeper in the next slides. And you can use that easily to set up already your robotic application. We provide you with some meaningful getting started examples and also extensions into the cloud services that we offer. Also in Robomaker is the simulation environment that you can use to create your own simulations and scale them to thousands of simulations running in parallel, giving you the ability to shortcut your development time quite essentially. And last but not least, Robomaker has the capability to offer you fleet management. So when you do have robots outside in the field, how do you update them? How do you monitor them? How do you make sure that they are all functioning as you intend them to do? This is something that you can do with Robomaker and fleet management. As I mentioned, under the core, when you're doing the development, it's using the Robot Operating System, or short ROS. ROS is not something that AWS developed. ROS is an open source framework that you can use as a meta operating system for your robot. Now, what does meta operating system mean in that case? It's not an operating system as you would normally understand, like Linux or Windows, that offers you abstraction on top of the hardware and offers you drivers. Rather, it is an abstraction on top of the operating system that allows you to create different channels for communication, that allows you to send messages between different parts of the process, and which you can use to create a robotics application on top of it. This is how ROS works under the hood, and this is just a generic example, but I hope that it will make the use case of ROS more clear in this case. ROS applications consists of nodes. A node can either be a publisher, meaning something that sends information into the network of ROS nodes, or a subscriber, meaning a node that listens for information. And these messages are sent through topics that you can register when a node comes up, for example, and that other subscribers can subscribe to. How do nodes find each other? Well, every node, once it has been started, its first task is to register itself with the ROS master. The ROS master is a special node that is responsible to act as a discovery service for the nodes. So when my subscriber wants to talk to a specific publisher node, it will first ask the master for the IP address and the port where this node is located, and then it is able to connect to this. The ROS master also acts as a parameter store. So you can use it, for example, to store calibration information or configurations for the nodes themselves so that you do have them at the central place. Since, in essence, this is a distributed mechanism, what you can do, you can also divide these nodes across different compute resources. So you can have, for example, the publisher just sitting on the master, just sitting on the robot itself, while there is a subscriber that's sitting on your laptop. And you can use this, for example, to create a connection directly with the robot so that you can see the output of the camera on your laptop, that you see the metric information on your laptop, and that you can also interact with your robot directly through your laptop without having to go to the robot and hitting some switches or buttons. Right? And this works nicely, especially when the laptop and the robot is in the same private network. Right? And this is what ROS tries to do. A node in itself is just a process. Every node is a single process that needs to be run separately, and in this case has no other reliance to the robot other than it does need to know where the ROS master is. Right? So to show you some code, and since this is a level 300 talk, this is how a publisher, a simple publisher, would look like in ROS using Python. ROS has two runtime or language bindings. One is Python, and the other one is C++. Since we are talking about embedded systems with low resources, this makes sense. This is a typical example of the ROS publisher implementation. On line 1, 2, we do have the standard imports. In line 3, we define a publisher, meaning that we would like to create a topic. In this case, this topic is called chatter, and string is going to be the message type that's going to send into these topics. Yeah. As opposed to potentially message brokers that you have previously seen, the ROS nodes are strongly typed, meaning that you have to define the message type of the message just that are passing through this. Next, in line 4, we are creating a new node. This is called talker in this case, which we are registering to the ROS master in this case. The address of the ROS master is defined through the environment variables. In line 5, we just create some environment setup. In this case, we say that the while loop that's going to come next should rotate with a frame rate of 10 hertz, meaning that we will not send endlessly. We will have a little bit of sleep time in between sending publishing information. And this is typically to simulate here, in this case, the fact that when you do have sensors that typically a robot would use to, for example, detect the velocity or detect the range to an obstacle, these will not emit sensor information like every microsecond or every nanosecond. Every sensor has its own speed on which it can deliver new information, and this is to simulate this here. And what we are finally doing inside the while loop, we are just sending a hello world to this topic by publishing it and then sleeping 10 hertz until we are sending again. On the subscriber side, this looks pretty similar, and also I would even argue to say even a little bit easier than what we have seen before. Same here, we do have on line 1 and line 2 imports that we need to make. Then we define a callback function that should be triggered when a new message arrives. On line 5, we are initiating a new node. In this case, we are calling this node the listener. And then we subscribe in line 6 to the same topic that we defined earlier when we have created the publisher. Here it's called chatter. And define that the message type is going to be string that we expect, and define the callback to be invoked whenever a new message is received. And then we spin. This is basically all there is to it. Right. Now, why ROS? ROS was created 2007 and was primarily used as some sort of mean to create a standardized framework that can be used for robotic development purposes, specifically for academic purposes, but has since then gained a lot of traction, and there is a well-supporting community around ROS that helps and aids in the development of ROS and creates also pre-packaged nodes and business logic that you can use on a lot of use cases, and has support for a lot of sensors that are out there to bundle them inside your robotics application. So when you're using, for example, a Raspberry Pi camera, there is a high chance that you will find already someone who has created a node that you can integrate directly inside your project so that you can leverage that. AWS choose ROS for its simplicity, for its availability, as it is an open source software, and is actually presented now inside the technical steering community of the Open Source Robotics Foundation, who is guiding the development of ROS inside the future. We are doing investments to provide long-term support for ROS 2. ROS 2 is a new version of ROS that is already available, and adds additional functionality on top of ROS 1 that we are currently supporting inside Robomaker. And we also invested to increase the ROS 2 packages available right now. So right now, for example, we are driving the migration of 113 critical packages from ROS 1 to ROS 2. Right? And we are also helping in the security and logging design of ROS 2. So how does this come back now to ROS? ROS is the underlying framework, robotics framework, that is used inside Robomaker to develop your robotics applications. On top of that, we provide you with cloud extensions for us that already give you native capabilities without having to code them yourself. But of course, you can also extend ROS with your own capabilities, with your own code, to further leverage AWS services, and there are just some on the top of here explained. So for example, Lex and Polly, if you want to create a voice interface for your robot, or on the far right side when you want to leverage CloudWatch, for example, for monitoring purposes. We provide you with Robomaker already some pre-packaged connections that you can use. Lex, Polly, I already mentioned, but we also have the capability. You also have the capability to use Kinesis video streams without having to do any coding at all. You can use recognition to detect, for example, objects in the camera of the robotics device, and also, of course, CloudWatch for logging and monitoring. Under the hood, how does the CloudWatch ROS package look like? So the CloudWatch ROS package, as we have seen before, and is common inside ROS packages, consists of nodes. And this is also what the ROS package does. It defines nodes through which you can send your metrics, for example, battery stats, or how much distance the robot traveled, that can be aggregated into a CloudWatch metrics node, which then, by default, goes into ROS out. ROS out is basically the standard out, where you can send logging information. If you're developing this without the cloud, this is what you have there already. If you want to use that inside the cloud, and of course you can create your own logic on top of that. If you want to use that with the cloud, what you can do is provide either stored credentials or temporary security credentials that will allow this CloudWatch metrics node to send the information to the cloud, to Amazon CloudWatch in this case, from which you can create dashboards, you can create alerts, you can create actions which you would like to take on these alerts, and then interact with the robot or interact with its maintenance later on. Let's talk about IoT here in this case. For those of you who are familiar with our IoT service offering, there is IoT Core, for example, which allows you to create a message broker and connect different IoT devices, again, through the means of topics by publishing and subscribing to them, which is, of course, pretty similar to the way that we have just seen how ROS works. So it's a perfect match when we're talking about that. What can be achieved through collaboration through IoT services? What we have seen before, the ROS master and the ROS modes, are separated per robot. So every robot has its own master and its own control nodes, right? ROS 1 currently does not allow you to have multiple masters and to also have multiple nodes per process, but this will eventually change also with ROS 2. But right now, let's talk about use cases first. Why do you want to use connected robots? Well, one of the main reasons is collaboration. In this case, we do have, for example, 2 robotic drones that can be autonomous, that can be used, for example, to identify landmarks while they are flying over some ground. And we can use these landmarks then in a collaboration to detect if the robot on the left-hand side and the right-hand side have seen the same landmark and are the same equal distance away from it, to create, for example, maps, to map dynamic environments, to map environments where humans, for example, cannot go because there would be a health hazard to them. Okay. And this is something that you can achieve with IoT Core. As I mentioned, in its core, IoT Core offers you a managed service that allows you to connect devices easily and securely with cloud applications. Right? We do give you, with IoT Core, a device gateway that is able to understand HTTPS and WebSockets, as well as MQTT, so the Message Queue Telemetry Transport Protocol, which is effectively created to allow embedded devices with limited network capabilities to connect efficiently to other remote devices. Next, we have the message broker. Through the message broker, you have the capability to publish, subscribe messages, but also a rules engine that you can use to transform the messages and send them to different AWS services, which are shown here on the right side. But of course, you can use the publish, subscribe mechanisms also to connect devices that are not sitting inside the same network, right? That are not sitting inside the same environment, and to help them interchange information as they go. Another service that can help you there is IoT Greengrass. IoT Greengrass extends IoT onto your devices that are not sitting or do not have a connectivity to the cloud at the edge. Right? Let's imagine, for example, a mining robot that goes down into a mine where there is no reliable network, so it cannot connect back to the cloud. Still, you want that robot, for example, to communicate with other mining robots to create a map, for example, or to understand the environment. And this is something that you can realize through Greengrass. Greengrass is a service that sits at the edge, so not in the cloud, but at the edge, and you can use this to connect devices locally on the edge, but also to connect back to the cloud again when the device itself becomes near to a point where it has connectivity. Okay. So both with IoT Greengrass and IoT Core, we are able to extend our robots in a fashion that they can be collaborating across vast distances and even through possibility areas where no internet connectivity is available. There is actually also an IoT Bridge example available, which is currently not inside the standard Robomaker, but you can find that available, which has been developed by the AWS Robotics team, which is currently under development. But if you want to use it, it's available on GitHub, and it provides you with examples on how to connect your ROS nodes to the IoT service. And actually, when we are talking about Greengrass, when you remember we mentioned earlier fleet management, Robomaker uses IoT Greengrass for fleet management. So when we have a new update, Robomaker is able to send an over-the-air update to IoT Greengrass that is then tasked to provision the robots sitting on the edge with the update of the software. Okay. So we talked about collaboration, we talked about development. But what about smarts, right? And typically when we are talking about machine learning, we like to talk about supervised learning and unsupervised learning, but there's even more to it, right? And especially important for robotics, there is reinforcement learning. Now, what does that mean? When we're talking about supervised learning, we are talking about training driven by examples that we provide. So when we provide, for example, images of cats and dogs, we label the images beforehand. This is an image of a dog, this is an image of a cat, and let the algorithm learn the weights necessarily, so when we give it another picture that's not labeled, that it's able to say, with that amount of probability, I see a dog or a cat in that picture. Right? So we provide the example. We provide the correct answers to this. This means that we have to have a lot of data, right? In all variations, in all fashions, small dogs, large dogs, logs of different color, in different poses, from different perspectives, so that we can actually, give a very, very high amount of different data through which, the algorithm can learn the best weights for its algorithm. Then there's unsupervised learning. Unsupervised learning, unlike supervised learning, there is no pre-made examples. There is just data. And unsupervised learning is tasked to find similarities inside the data so that we can detect, for example, different categories. So when we do talk about, for example, mobile providers, we would like to know, inside my customer base, how many people are using SMS, how many people are using voice services, what is the age of the people. And unsupervised learning helps us to find these categories, and we can use these categories later on to find, for example, outliers. Right? Is someone not fitting inside the categories? Or when we are talking about IoT and predictive maintenance, for example, is a machine behaving the way that we expect it to behave? Or is there, for example, a motor that's broken and needs to be replaced, and we can inform our maintenance supporters early on to get in touch with the customer to replace it before something seriously breaks? And then there's reinforcement learning. Reinforcement learning is learning through consequences of actions in specific environment. Let me give you an example of this. I'm pretty sure that, everyone is already doing reinforcement learning. It's a way that humans learn. We learn by trial and error. We try something, we fail, we learn from it. Right? This is how we learned from the beginning of the moment of our birth. Right? We try something, it hurts, we don't try it again. Or we try it from a different angle. Right? And the way that we are doing this is our brain rewards us when we are behaving positively, or it is reinforced by our environment, so for example, the dog holder in this case. And we don't reward negative behavior, and actually, in some cases, we punish it. Right? And this helps us to calibrate. This helps us to understand the rewards in regards to our actions. Every action has a consequence. It has either a positive reward or a negative reward, and ultimately we would like to train our dogs to be, to hear to hear to our commands and to adhere to it. Right? So use cases for reinforcement learning, financial training, right? When should I buy a stock? When should I sell a stock? Right? Buy, and the reward is good, positive signal. Buy or sell and the reward is negative, bad example. And this is how we can train our environment here in this case. Autonomous cars, try to stay in a line, right? This is something where the supervised learning by itself will not work anymore because the environment is changing. There is no data set that we can provide to it. Every street is different, right? Every street is different. The velocity of the car might change. There might be certainly some obstacle that's on the road, and we have to navigate around it. This is something where supervised learning fails, right? Because it can deal with dynamic environments. Fleet logistics, another example. Data center cooling. So what is reinforcement learning? And first off, typically what we do inside reinforcement learning, we first describe the problem as a model. In case of reinforcement learning, this is called the Markov decision process. The Markov decision process says there is an environment, right, which is represented by a state. Right? So for example, if I'm in a maze, the maze is divided into cells, the robot always stands in one of these cells. This is the state. Robot is in cell 00, for example. Right? In this state, the robot can take an action. The action could be drive forward, drive left, turn right, turn left, stop, do nothing, take a picture, whatever it is. Right? And what we would like to do is, especially sticking with the example of the maze, we would like the robot to reach some kind of goal. Get outside of the maze, for example. Right? And what the model should do, it should allow us to reach that goal in a way that we reward it with something. Right? So in a typical case, this could be, for example, try to reach the goal with the lowest amount of steps. Try to reach the goal within a certain period of time. If you're reaching it, good, you are getting rewarded. If you're not reaching it, if you're not taking the shortest path, then punishment. And how we define this is up to the environment that we are trying to simulate, or up to the environment that we're trying to teach the agent, the robot in this case, navigate. Right? So how does deep learning happen here? We have the environment. The robot itself receives information from this environment. It receives information of the state, sticking with the maze, in which cell am I in, and it receives information regarding the reward, how much time has passed. And given this information, the robot can take an action. Move, stop, move right. This is then, again, fed into the environment, which, of course, yields a new state. If the robot moves forward, then it's not in cell 00 anymore, but maybe in 01 or 10, depending on how you define your axis. Right? Again, we receive a new state and a new reward, and what we try to do with this, by taking different actions, is to find a policy function which tells us, if I'm in state XY, then turn right, because it has the highest possibility of giving you a positive reward. Right? On the other side, we are trying to optimize the value function. The value function is, what steps do you need to take to get the maximum cumulated reward at the end of the session? Right? And this works differently depending on which state you're in. So for value approximation, for example, where we do have a race to do, for example, with Deep Racer, right? We need to consider all of the states and actions and outcomes that are possible there. And there could be many, right? There is velocity, and even a slight change of velocity, even a slight change in the friction of the course that the robot is driving can yield to vastly different results. So it's nothing that we can do with supervised learning, right? The solution is to approximate a value. Given the circumstances, what is the best choice that you are able to do to get the most reward out of it? Policy approximation is another example. Policy approximation tells us, ideally gives us a map, right? A map that the robot should try to use to navigate around the environment. And we can use supervised learning to train a policy function, but how do we know it is a good policy function, right? Ideally, because it gives the highest reward. If I'm in that state, and this is an example from Dota 2, use this spell, for example, or try to go to this item presser to give you some kind of impact. So we try to use the one step that gives us the highest reward. And depending on which you choose for your reinforcement learning algorithms, it depends highly on the problem that you're having. When we're talking about a maze or a chess game, this is a deterministic environment. It ends. At some point, it will end, either because the time runs out, or the game is lost, or game is won, or we are going out of tracks, or we are reaching our goal. At some point, this epoch will end, right? On the other hand, policy approximation is great for environments where you do not have an ending, a terminal state, right? So policy approximation can be used to find something that will even, keep going, even if the action space is continuous, so there is no end to it. And depending on your choice, you can use different algorithms. Some of them are Q-learning, deep Q networks for value approximation, and policy gradient and proximal policy optimization for the policy approximation algorithms. So coming back to AWS, how does that all fit into cloud robotics? We have a service that's called SageMaker. SageMaker is a fully managed service that allows you to create your entire machine learning workflow to label, prepare your data, choose an algorithm, train the algorithm, tune and optimize it to your needs, and make predictions with it. Right? At reInvent last year, we introduced an addition to that, which is called Amazon SageMaker RL, reinforcement learning, which provides SageMaker with additional prepackaged reinforcement learning toolkits that help you to get to reinforcement learning faster. We also provide you with hands-on examples and notebooks that you can leverage. And some of the prepackaged tools that are available here is, for example, Intel Coach, the Ray Lib. We provide you with OpenAI Gym, and of course, MXNet and TensorFlow, and we support open source and commercial environments. And this is now where it gets interesting. As you remember, we talked about you need to have an environment that you can send to this machine learning algorithm. So it means that this environment needs to be a simulation of the real world that you are trying to teach your robot to navigate. And this means that it should have the possibility to simulate physics. It needs to have some kind of mechanisms to detect collisions, for example. You need to be able to tune it, to configure it to your likings, and to also tune your model of the agent itself, so the robot itself, as it navigates through it. Right? As of today, you can use many existing libraries, but you have also the possibility to extend real-world problems with other open source tools that you can bring in addition to that, to AWS. So what we provide is a connection to AWS Robomaker and Amazon Sumerian, for example, where you can run your simulations. But we also support that you bring your own environments as long as you stick with the APIs that are provided by the machine learning frameworks. So this is how the simulation architecture would look like with Robomaker. Robomaker is sending information from the simulations to SageMaker, which is then evaluating them and training the models. In addition to that, you can stream these environment images to S3, send the models to S3. You can send the video feeds to Kinesis video streams, and you can collect metrics through Amazon CloudWatch. How is simulation done inside Robomaker? Robomaker comes, in addition to ROS, with Gazebo implemented. Gazebo is an open source robot simulation tool where you can create your own environments, create the configuration for these environments, like in this case, the deep racer track, and use that to learn an approximate policy and value functionality. And this is how it looks like when we are looking diving a little bit deeper in this. This Gazebo environment that we have seen is generating images. These are the observations, right? These tell us where the robot is inside the environment and what it currently sees. And depending on that, we can take a step, move right, move left. Right? And these are the actions that we send back to the simulator. The simulator generates a new image and a new reward, which is then given back to our agent. And since these are images, we can use convolutional networks to detect, for example, if the robot is in line or stepping outside of the line of the boundaries, and use that to approximate the body function over time. Okay. So in closing, we have talked about many services here, primarily Robomaker, which helps to accelerate development time with zero infrastructure provisioning. We have talked about IoT Core and Greengrass that can help you build collaborative robots that are well collaborating with each other, but also with humans, right? And then we finally talked about SageMaker RL, which helps you to create reinforcement learning models for your robots to actually make them autonomous and drive and act in dynamic environments that may change over time. And with that, I would like to close the session. Thank you for your time. Thank you for your attention. I hope that you had a great AWS Summit in Berlin this year, and we hope to see you again next year. If you do have any questions, I will be here. Please feel free to drop by. Thank you for your attention.